here and today is from bag of words to transforms. These are two main aspects or initial points of processing text and the state-of-the-art technology of processing the text. So let's start. Okay. Here is the outline of today's talks. I'm going to talk first a little about NLP. This could be something that you have already seen. Then I'm introducing bag of words. I'll talk about word embeddings also, and then get more detail about language models, and finally transformers and other aspects of learning, some transfer learning. So let's see what's the language. Okay. So as most of us know, vocabulary consists of a set of words. A text is composed of a sequence of words from a vocabulary, and a language is constructed of a set of all possible texts. Languages can be divided into subgroups. We have natural languages like the languages spoken by people, English, Chinese, Persian, Swahili, French, Spanish, Arabic. These are all natural languages. These are languages that spoken by human beings. And also we have some sort of other artificial languages. So those languages that are man-made languages. One of the famous ones is Esperanto. Esperanto is a language that some linguists try to generate new language from scratch, building a vocabulary for it, building some grammar for it, and then ask people to try to speak and write in this last language. You can find about Esperanto in the Wikipedia. If you can find more detail about it if you are interested to see how it was developed. And another kind of artificial language is computer languages, right? Those are like programming languages like C++, Python, Java. Those are all man-made languages that would develop to communicate with computers. And the actual dreams of human beings from very long ago was that, but to invent something and that he or she can communicate with machines. In that way, machines can process our daily mail, translate language accurately, help us manage, summarize, and aggregate information, use speech as UI when it's needed, and also other different other tasks. But it's not that much easy, right? Because the language, and here specifically the human languages, is complex, ambiguous, flexible, and subtle. So it's not easy to communicate with machines. So humans try to, from 60, 70 years ago, people started using artificial intelligence to find some ways to communicate with machines. So they invented natural language processing tools and software. Natural language processing, or which these days we call it as NLP, is a subfield of artificial intelligence. It's an interdisciplinary subject between computer science, linguistics, statistics. And the main goal of natural language processing, or NLP, is aim us to build intelligent computers that can interact with human beings like a human, right? So we want to communicate to machines, and because of that, we need find sort of language to communicate with machines. The fundamental goal of NLP is to deep understanding a broad language. And by understanding, we mean not just something that we can process strings or keyboard magic. We want something that we can understand and get the concept and semantics from the text that we have that, and we communicate through that with machines. So there are a lot of NLP tasks that most of you, I'm guessing that most probably seen some of them and using some of them in your daily routines these days. So the main one, for example, and that most of you have seen is spell or grammar check. When you are texting someone or writing a Word document, so you have seen the spell check, right? The other thing is that word prediction. When you are searching Googling something, where you have seen that Google is trying to predict your next input. Information retrieval and information extraction are other two types of NLP tasks. Text classification, name entity recognition, text summarization, text generation, translation, and question answering are other sorts of NLP applications. And by the way, please stop me whenever you have a question. Don't hesitate to stop me. But as we said, natural language processing is not as easy as we were thinking. It has its own challenge. Some of the main challenges is that paraphrasing. There are different words or different sentences that express the same meaning, right? For example, fall and autumn are both different words, but they exactly mean the same. Another problem is ambiguity. One word or sentence can have different meanings. For example, fall can mean that falling from somewhere, down, or it's the name of one of the seasons of this year, right? Bank can refer sometimes to institute or to building that people put their money there, or can somehow in another sentence refer to a place that is very close, just the side part of a river. Fly, and I think that you're, a lot of words in other languages that have different meanings in different places. And this is a famous, actually, plot, a famous image that about this sentence. I saw the man on the hill with telescope, right? So you can infer a lot of meanings from these questions if you don't know any other side information, right? Who had the telescope? I had the telescope, or the man that I saw. Who was on the hill? I was on the hill, or the man was on the hill with the telescope, right? And this is something that makes language very ambiguous. And this ambiguity and paraphrasing and all challenges makes processing the languages and understanding the human spoken language is very difficult. It's not, as I told you, it's not a very easy task. So let's see that how is just workflow of NLP. As I told before, NLP is a subject under the subject of as a part of artificial intelligence and machine learning process, right? So for a machine learning task, most of you should know by now that we have two phases, right? Two main phases, training and testing. Suppose that you want to classify a text or do some sentiment analysis. So we have a data set, we put it into different sub-data sets, we call them training data set and testing data set. So for training, then we start pre-processing our text. By pre-processing, we means cleaning our text from some punctuations, put some and some unwanted characters, split words, counts the word frequency, and so on. Then, from the clean text, we extract some the required feature and make some vector, and then input and feed those extracted features to training classifier, to machine learning classifier, machine learning model. And when we train that machine learning model, then we can do the same process over our testing data set and apply and deploy that model over our testing set. So let's see through these steps step by step and see that what are the main algorithm, main approaches and main methods that see. First of all, processing and cleaning. By pre-processing, we mean that we need to somehow clean our data from some unwanted characters and unwanted words. We can remove non-alphanumeric characters, for example, exclamation, question mark, comma, dots, underline, and so on. Then we can convert to lowercase, split our text into individual words, remove some stop words that appear a lot in each text but doesn't have any specific meaning in some sense that cannot indicate the class or purpose of the text. And then we can do something called it stemming. And also there's the same and a very similar step called lemmatizing. By stemming, we mean reducing inflected words to the own word stem. For example, if we have argue, argues, argued, arguing, argument, the stem of all of these words is argue. So we can replace all of these words with argue, and then we have a clean text, right? And behave with all of the words. All of, for example, these words that are based on argue as the same word. And so when we have a clean text, we start doing some feature extraction. As most of you know, original text or original data usually is raw text. But to fit it to computer, we need to convert raw text to some numbers, right? So first of all, we can tokenize data, convert each sentence to a list of tokens, and then start transferring those tokens to some numerical values, because machine learning algorithms need numerical data for the task. And this process of converting words or tokens into numbers is usually called vectorization. We have raw text, we vectorize raw text, and then extract some features in the shape of some vectors, numerical vectors, and because of that, it's called vectorization. The most basic, and then we want to put every token of our text in a space that close words come to together, very close in that space. And those words that are not close, you get it far away from each other. By closing and far away in that space, we usually by meaning, right? Those words that have the same meaning, we want to put them in the same place, very close to each other in that converted or transformed space, and those that doesn't have any relation to each other, we want them to have a very far distance from each other. So there are different approaches for doing the vectorization. The most basic ones are bag-of-words approaches, and some more sophisticated ones are board embeddings. And we are going to review those approaches here today. Bag-of-words approaches uh, consist of one-hot encoding, count vectorizer, and TF-IDF. And for word embedding, we have word-to-vec, fast-vec, and glove. So to see how each one of these approaches work, let me introduce a very simple data set. Our data set consists of just four sentences. One is he's playing in the field. The second one is he's running towards the football while the football game ended. Then the football game started, and finally it started raining while everyone was playing in the field. So we make it, first of all, we make a dictionary out of this small corpus. And by corpus, we usually refer to text data sets as a corpus. Our small corpus has 17 unit words, the ones that you can see here, right? From ended, everywhere, field, football, till, towards, and was, and why. I'll let you sometimes to check the sentences and see the words in our dictionary. Okay. So the most simple one is one-hot encoding. It's the most strict one. It models each text and each document as a very long vector. Dimension, the length of our vector is at the length of our dictionary. Each feature, each word in our dictionary represents a feature in the vector of each document. And then we'll check that for every single member of that feature, which actually is a single token or single word, we check that if that token or that word appears in our document or not. If it appears, we may put it one there, but if it doesn't appear, we put 0 on the place that refers to that word. So the steps of one-hot encoding is that first of all, we identify the unique words and make a dictionary. And then for each text, assign a vector of size of the dictionary. In that dictionary, indexes are our words. And assign 1 to each index if it presents in the text and unless set it to 0. For example, remember our dictionary, and suppose that we have this sentence. This is one of the sentences in our corpus, right? He's playing in the field. So we have this 17 length vector. The first part of our vector, the first member refers to as ended. Is ended appear in this sentence? No. So we put 0. The next one is word is. Is appears in our dictionary? No. The third, oh, sorry. We check it from here, right? This is our dictionary. So the first word in our dictionary is ended. Ended appear in our sentence? No. So we put 0. The second one is everyone. Everyone appears in this sentence? No. The third one is field. We have field here. So we put it 1 here. We don't have football, we don't have game, but the next one is he. We have here, we put 1 here, and so on. And till the end, for example, We have playing, so we put one here. We don't have raining, running, X in the paragraph. We have 6 feet, 5 I, 4 and so on. And because of this similarity, we call it bag of words approach. But the main problem with count factorial is that it doesn't consider the importance of the word across the complete list of the sentence. For example, he is in 2 sentences. There's no useful information in different between these 2 sentences. So we need to somehow weight our different sentences. And because of that, there is this approach, we call it TF idea. It consists of 2 parts. TF, which stands for term frequency, is the number of times a word appears in a given sentence. And we also add another part. We call it inverse document frequency idea. Is the log or the actual total documents divided by documents in which the word appears. So if we have a word, for example, like that appears in most of our sentences, we want to decay its importance because you can see it in all of the sentences. So it doesn't make any difference between different sentences. But if you have, for example, a word football that appears in one sentence, in one document, and a word baseball that appears in other documents. So they both somehow represent that, okay, this the first one appears a lot of football inside that. But the word football doesn't appear in other sentences or other documents, so it put a lot of words on a single document. So for each word and each word X and document Y, we define WXY, which shows that the importance of word X inside document I, inside sentence I, inside text Y. It consists of 2 parts. TF, term frequency, the number of times that word X appears in document Y, multiplied by log of this part, N over DF of X, we call it ID, inverse document frequency. N is the total number of documents that we have. In the previous example, for example, N is the total number of sentences we have because each sentence represents a document. And DF, document frequency, is the total number of documents that have word X inside it, that contain word X. And for each single word and for each single document, we calculate word WXY and fill out the vector representing that document or that sentence with these values. So the steps are like that. We have identified again unique words, make a dictionary, and for each text assign a vector of size of dictionary. For each index word, for each word in our sentence, we calculate the value of TF-IDF and update the corresponding value in the vector of that sentence. For example, for this sentence displayed in the field, we had already seen that we have already 5 sentences or 5 documents. In 2 of those documents, this word he appears. The number of times the word in the first document is 1, and the number of times it appears in the first. And the total number of tokens in first document. By document, I mean this sentence, right? Displayed in this way. This document has 6 words, and the word he appeared just once here. So the term frequency is 1, it appears once, And inverse document frequency for IDS is log of n over n. Log of or here n is 4. We have total 4 sentences. The word he appears in 2 of them. So we calculate log 2. And 1 times log 2 is this value, right? 0.6931. And sometimes, somehow, for our calculation, we add 1 to it because if this n is 0, we don't want to put 0 division of this fraction, right? So the field vector or the generated vector of this document is like this one. But all of these bag of words approaches have some common shortcomings. The main one is that they lose the context. Similar words, similarity of words is not considered. And it's also not in order of words in a document is not taken into account with the bag of word approaches. Because of that, people start from something more sophisticated approaches that somehow include the meaning of each text, each word in the similarity matrix. And then come word embeddings. Word embedding is a collective name for a set of language modeling and feature extraction techniques in NLP, in which words and phrases from a vocabulary are mapped to vector of real-life numbers. If you remember, for the bag of words approaches, the vector size was equal to the size of our dictionary, right? So, for example, for language like English, that we have almost 50,000 words, the vector size should be a vector of length 50,000. But here we want to represent each text in very smaller vector like that. Somehow we convert or we represent each document or each text with only vectors of size 100, 200, 300, something like that. So using word embeddings, we can capture the meaning of words in a document. We can have both syntactic similarity and semantic similarity, and we can contain the relation with other words as well, right? So the main approach is like that. One of the main approaches called word to vec. Word to vec is defined by Google, and the main idea was like that. Using word embeddings, we want to say the relations between words and also the similarity. In that case, for example, if we represent each word as a vector, so the distance that we want the vectors representing things and the vector representing man should be also pretty similar to the distance between vectors showing woman and vectors showing the vector that is representing the word queen. So if I say the king to man is similar to queen, so this distance should somehow represent to the word woman. It also needs to, it keeps verb tenses. For example, walking is transferred and it's very similar or very close in the space of this end word and that needs to walk. Swimming also is very close to swim. And also, for example, for country capitals, If you have these words, Spain, Italy, France, Germany, and we take the embedding of each of these words. So the distances, for example, between word embedding of the vector embedding of Spain to the vector embedding of Madrid should be almost the same as the distance between Italy and Antwerp, because this distance shows a relation which we call capital, right? So it should keep also the same, should have the notion of capital should be also the same for different word pairs. Turkey, Ankara, Russia, Moscow, and China, and so on. So we can to generate these word embeddings, we can use and start using neural networks. Neural networks based embeddings are a set of neural network models that have the aim to represent words in vector space. To transfer a vector of, for example, size of 50,000 to just a vector of size 200, here we use neural networks. And this transformation should keep similar words in meaning and put them close together in vector space, and also put the dissimilar words as far as possible from each other. And as I told you, one of the main approaches and main algorithm is called word-to-vec. It means word representation in vector space. It was invented by Thomas Micallef and a group of research team from Google. And it's still one of the most popular techniques to learn word embeddings. Word-to-vec approach uses a two-layer neural net. The inputs are the text corpus, and the output is the set of vectors representing each token or each word in the corpus. And a well-trained set of words, vectors will place, as we mentioned before, similar words close together, and the similar words far from together. So they use two different models for this embeddings, two different network architectures. One is called CBOW, continuous bag of words, and the other one is skip graph. In CBOW, the neural network takes a look at surrounding words, so it has two layers: input layer, projection layer, and output layer. You can call it three layers, right? As the inputs, they fed each sentence to the network, but remove one of the words from inside the text, and the output should guess what is the word that is removed from this sentence. So the network looks at different words around the hidden words and try, based on these surrounding words, try to guess what is the word that was hidden or removed from this sentence. The other is skip graph. The skip graph, the neural network, the task is somehow the other way of guessing the output. Here we only have one input word, and the network try to guess the surrounding words of the sentence. From each sentence, we fed only one word to the network, the training phase, and show it that the surrounding words should be which words. And then the network is trained to guess the surrounding words that comes for each single specific word. So here is both architecture in the same picture. For example, here in CBOW, we have pineapples are hidden or removed and yellow. And the network should guess that the hidden word or the removed word it was spike. In the skipgram, we fed the spiky to the network and it starts guessing that okay, the surrounding words are pineapples, are, and yellow. And based on this training phase, the network learns the embeddings, the vector representation, the smaller vector representation of each single token. And after learning and after training phase, then here is an example. For example, we have the mouse ran up the clag, and again we have the mouse ran down. Here we can see that we have the mouse ran up, clock down. These are all words in our dictionary. We put this sentence to our embedding layer, and this is the generated embedding the generated vectors of each for each token. And check here that we have 6 words, but and definitely a lot of other words, but the number of the size, vector size of each word is only 4 here. And for example, we had word 1. The first word was the here. So we have same embeddings here. 0.26236 minus 0.141, and here it appears again, right? And then we have word mouse. The embedding of the mouse is this one, the embedding of the mouse. And here is another example. So we trained word to make a model and ask, for example, for most similar words to queen. The model then output a list of most similar words to queen. Here, the first one is king, but here the other 2 ones are doubles and twins. Why? Because most probably the text that we train our embeddings are our networks with for the embeddings were text related to home appliances and home tools. So double and twins and bed and sofa, sofa bed, they're all related words related to beds. And as you know, in the vocabulary of sofas and beds, we have king beds and queen beds. So in that context, if you ask for similar words to queen, definitely the first one is king. But then instead of, for example, a soldier, or instead of other, or for example, other words related to monarchy, here appears some other words related to home appliances and beds and sofas. And here is the word for coffee. The most similar words in our text, for example, similar words with coffee was tea, coffee maker, teas, espresso, biscuits, pastry, pot, cappuccino, croissant, and so on. So if you're using Python language, there are different libraries in Python. For processing, you can use beautiful soup, regular expression, and NLTK for vectorization. There are this famous library, Skylern, for machine learning, different machine learning tasks, and one of the sub is also part of the library, like feature extraction. Using feature extraction libraries from sklearn, you can use TF-ID vectorial account vectorizer. For embedding, you can use this library called Johnson. And for training the model and classification, again, using different parts of sklearn library. So, any questions till now? So we have talked about some basic approaches to somehow represented text as a vector and for text representation. Now we want to talk about some more complex and the state-of-the-art approaches. And most of these approaches are based on deep learning. There are basic difference between using machine learning, simple machine or traditional machine learning approach for text or other tag sort of data and deep learning data. And the main difference is like that if you are using some sort of traditional machine learning algorithm or models, you need to, first of all, as we mentioned here and we talked earlier, we need to extract some features from our inputs. These features could be some vectors based on bag of words, for example, TF-IDF or some embedding vectors. And then we fit those features into some classification models and get some out. But by using deep learning, we somehow combine these two steps, feature extraction and classification together. Most of the deep learning architecture, we also do the feature extraction parts inside them and themselves. So we don't need to do this embeddings or doing this feature extraction as a separate phase. At the same time, we somehow embed the input, extract features, and do the machine learning task that we want, for example, classification, using the same architecture and the same network. And for a specific NLP task, here is the different NLP workflows with deep learning. As we had talked earlier, for traditional machine learning methods, as we get input data, we need to pre-process data, do feature extraction, model establish, and then output result. But using deep learning methods and deep learning architectures, we somehow combine all of these three steps in a single step of the somehow encode all of these steps in the architecture of our deep learning, and the whole network, while training, learns to somehow do the pre-processing and feature extraction itself. And when we are using deep learning, when we should use traditional algorithm, it's based on the amount of data that we have. If you have less amount of data, so most of the times, maybe using traditional algorithm are better. They are faster and they are easier to use. But as the number of our training data increases, the accuracy or the performance of deep learning or fast traditional algorithm, machine learning algorithm, and it's better to use deep learning. Here I'm going first talk about some notion of NLP, which is called language model, and based on language model, see that what are the state-of-the-art techniques for that makes a large language model. A language model tries to capture the pattern relationships within a language, right? So it somehow learns to predict about what words are likely to follow given context. For example, if I give you the sentence, once upon a something blank, most probably most of you will fill out the blank as time, right? And not automatically. So The primary function of a language model is to calculate the probabilities, these conditional probabilities that if a part of a text is given, for example, once upon A, which of the word of language is coming next. So for each combination of words together that makes a sentence, the language model tries to somehow estimate this probability, this conditional probability that in general pattern, in general form, if you have n words, what is the probability that word n comes after word 1, word 2, word minus 1? Again, like this once upon a blank, what is the probability of uh, p of time given x once upon a time? Is it the same as p of armadillo given once upon a, or which one is higher? So in complete language model can somehow estimate that, okay, this probability should have higher values than this value of this probability should be much higher than any other words that come instead of time. Here is the evolution of NLP models that using the for language models. We saw the bag of words, then became to word embedding. Then there are some neural network-based models, recurrent neural network, LSTM, long short-term memory-based models, bi-directional models, and then comes attention model-based and transformers. And here I'm going to talk about the other side of this evolution diagram about transformers and what are the attention-based models. So in general, we can divide language, we can have two approaches to model a language. One, which is older one, is called statistical language model or in-gram models. In that, we can, for each single word, as we talk about, we calculate the conditional probability. That, for example, if we are given where are we, these are context, these are called context or previous words. What is the probability of going? And how we can predict we're going, right? For that, we should calculate this probability of P of S equals to of P of where times P of R given where times P of or probability of V given R and where and so on. But another approach is neural language. In that case, instead of calculating or estimating its single probability of the model, we give all of the text into a language, into a neural network, and the neural network tries to learn that what words should come next. And then if we give this sentence, for example, the color of the sky is to our network. This is the task of a trained neural network to predict that this next word should be below with 91% probability. For a neural language model, we fed a large corpus of text to train the model. But usually the outcome of this training process is called pre-trained language model. This is a phase that we train a neural network based on a very large corpus of the text. But the outcome for the pre-trained language model is not fine-tuned for any downstream specific task. It can only somehow capture the patterns of the words inside the corpus. The model is equal to the foundation, and because of that, they are usually called foundation models because it can understand the natural behavior of the voice in the language. So here in this diagram, we put the large text corpus to the model, and then we ask the model that the TRV fountain is in the center of, and the model should guess the next word should be Roma over Buenos Aires, right? So to make it more specific and to make it more clear that how language models work, suppose that we have a very, very big typewriter, right? The striker for each single word instead. So in usual typewriters, we have a striker for each single letter. But in our typewriter, we have a striker for each single word. For example, if we make a typewriter for English, our typewriter should have 50,000 strikers, right? The task of our typewriter is that as I press one word, in the output, it should print or bring over the paper the next word that should come after the word that related to this strike. For example, for the here is general view of that typewriter, and I can somehow model that typewriter as a neural net, right? I have 50,000 words, so to each of these words and 50,000 strikers. These are input strikers or input words. And each word is connected to a striker, and each striker is connected to another output striker. That, for example, when I press striker related to once, it should print out upon in our output. But as you can see, it's a very, very large typewriter, right? 50,000 strikers in the input and 50,000 strikers in the output. So the total number of striker arms is 2.5 billion strikers. But this is the network that I want to train and to somehow model the English language. So I model the whole English language as a typewriter, and then model that typewriter as a neural network. And I told you, this is a very big network. The previous network is work for one single token or one single voice. Now, if I have to generalize it for bigger sentences, for a sentence that have three input words, so I should put each of those typewriters together, right? 50,000 strikers for word one, once, 50,000 for the second word, upon 50,000 for the third word, A, and I should make all of this connection, and then when I put one after one, once upon A, our typewriter should print out or bring into paper the word time. But as you can see, this is now going to get bigger and bigger and bigger. 50,000 fonts, and for three tokens for three words, 50,000 here, 50,000 here, 50,000 here, connected to 50,000 output strikers, I would total have 7.5 billion striker parts. So somehow I need to make it much smaller. In that case, it comes to large language models and neural networks. Here is a evolution of large language models. They started from 1967. They're somehow pretty, right? The first one was ELIZA. It was an algorithm and large language models invited in 90. Then comes another one. In 1988 comes uh, recurrent neural networks. Then about 10 years later comes long short-term memory neural networks. And then comes here. But the turning point was here in 2017 when it comes the notion of transformers were generated and transformers models was built. And after this time was that the other large language models like the BERT or GPT-based models, GPT-3, GPT 2.5, GPT-4 comes here. And this is the place that we are standing here. We have the large language models like Llama, Falcon, GPT-4, Lima, Bard, PAL 2 that we are using here. So as you can see, we have into a very, very long way. But as I told you, the turning point in this way that caused this to turn was here in 2017 that transformer models was introduced. So what are transformer models? Those are some language models, as I told you. It's a particular type of deep learning model that are usually trained on large amounts of raw text in a self-supervised fashion. What is self-supervised fashion? I will talk a bit about self-supervised at the end of this But in general case, suppose that you have an input, je suis étudiante. This is a sentence in French. Give it to a transformer models, and it generates its translation in English as an output, right? I'm a student. So we want to see what is inside this transformer part, what is inside this box. That makes it very specific. In general, what is inside this part, general architecture of transformer model, is consists of two separate parts. What is called encoder, and the other part is called decoder. The encoder part receives an input from the group text and build the embeddings, build the representation of its feature. So you remember the word embedding we talk about? This is main task of encoders here. And the encoder part is optimized to acquire understanding from our data. Then those embeddings are passed through the decoder part, plus some other outputs that we have. The decoder task is to use the encoder's features with some other outputs to generate an output for us. This output is usually the output probabilities of the words or sentences that should come later. And the whole model is trained and optimized to generate those outputs models. So what is encoded? The main idea of encoder was that a lot of words, word meanings approximately comes to the same things, right? For example, if you have these sentences, the king sat on, the queen sat on, princess sat on, the regent sat on. The reasonable guess should be true, because all of these sentences, they include a key word here, king, queen, princess, which is somehow are the same, or they all refer to the same concept, which we call it monarchy, right? So based on that concept, it's like that this one of the main sitting on the concept of monarchy is on the throne, and it's not on the toilet. So back to our typewriter example. So here there is no need to separate strikers between the king and throne, or we have a separate striker between queen and throne. We find similar concepts and use a common striker for them, right? So in our typewriter model, instead of having a separate striker from king to throne, from queen to throne, from princess to throne, so we have four different strikers. We can put all of these four different strikers using an encoder, because we are encoding the concept of monarchy, and use only one striker. So as the output, when I press the king sat on the next striker is throne. This is the same for the queen sat on and this is the same for the regent set. So the whole idea of encoder is like that again, generate some sort of word encodings. Back to that typewriter example, that as we can set up our typewriter or our network that with the same striker for the same concepts. And in that case, instead of only trigger a one striker arm, we can mash a bunch of strikers, right? And then each possible combination of the strikers arms could represent a different concept. Then, for example, if we have queen, king, regent, soldier, princess, they all represent concept of monarch. But another striker are the terms queen, kings, double, lining, sleeping. They all, for example, make a different striker for the concept of bed and so forth. So, for example, if we, instead of putting a single striker, we made 256 of them. Then we can encode and show each concept with a vector of 256. For example, king might be represented with this vector, this embedding, and queen might be represented with another vector. The only difference is like that in the second part, this is 0, this is 0.1, but all of the positions, they're almost the same. And here we can encode it, all the concept in only and all the concept is like that this amount 1.15 times 10 to the power of 76 can encode all of these concepts in just a single vector of size 256. So this was the task of encoder part. And we have also decoder. Decoder is like the other way. It gets a decoding and connected to single word and guess that what is the word representing that embedding of and that embedding. So for example, in our previous task, we had once upon A, and this is the task of decoder that if it reaches, it see this vector of 256 values, it decoded to do upon once upon a time. So in a transformer architecture, the transformer part, you have a stack of encoders. Input text is given to a stack of encoders. And then the last encoder send the given encodings to a stack of decoders. But as you can see, they are put in a serial format. But the last step of encoder, the encoding part is sent to all of these decoders, and each decoder receives two inputs, one from the previous decoder and one from the other decoder. So the task of our task is to train such a model that if we give it user étudiant as the input, it generates IMS student as the output. Inside of each of these encoders and decoders are two main parts. They consist of self-attention and a feed-forward neural network. This is the inside of encoder. Our decoders have another part like that. Self-attention, this is the attention. So I'll define that what is attention better. But just thinking is it just black box. This is the box that gets input from the previous or our inputs of the sentence that it gets to the encoder decoder attention. It receives inputs from the self-attention part and the encoder part, and then there's a feed-forward network. So this is the inside of each of those encoder and decoder. So let me go back and again. This is the general form of the transformer. We have a big model here, call it transformers. This model consists of two main parts, an encoder and the decoder. Encoder gets inputs, makes encodings, send them to decoder parts. Decoder gets inputs from the previous steps and also this our inputs and generate output. What is inside of this encoder and decoders? The encoders, they are all encoders are a stack of encoders. Decoders part the stack of decoder part, and each of these boxes is consists of encoder. General form of encoder is the self-attention plus feedback. Self-attention, encoder, decoder, and feedback. So, what is self-attention? What's the task of the self-attention part? The main concept that is used in the transformers models is this concept that's called self-attention. And this is the self-attention that makes transformers very specific. That caused that turning point to the history of language models. It was introduced, actually, the transformer models and the concept of self-attention was introduced in this famous, very famous breakthrough paper, turning point paper. It's called Attention is All You Need. It was published by some guys in Google in 2017, and it was really breakthrough in the development of language. I highly suggest that every one of you should find this. It's easily available. Go and just Google attention is all you need, and you can access the paper and try to read and understand it. So suppose that we have this sentence, right? The alien landed on Earth because it needed to hide on a planet. If I do mask the word alien, and I ask you that guess it. Because of it has landed, Earth, and planet. Because of these words, you can guess that, okay, most probably it's alien. If I mask out the word it and I ask you to guess that word, because of the word alien, you should most probably would prefer it over he or she because there is no human here. There's an alien here. So we use it instead of he or she. Also, the presence of the word earth helps to capture the word planet. Capturing these relations in a text is very important and makes the task of word guessing or word generated text generation very easy for us, right? And this is the main task of the self-attention part, the self-attention component that I show you in the architecture of transformers. So the basic idea of self-attention is that certain words in a sequence are related to each other, are related to some other words in the sequence, that those words are not specifically comes next to it, right? Those words can come somehow later on. For example, here, alien comes in fourth or fifth word before that. Also, those words can come after it, landed as or a very long distance from it, planet. So the words are related to other words by function, by referring to the same concept, by informing the meaning of each other. And in general, they are not located in a sequence of words very close together. Knowing these relations between words is very useful for prediction. And this is the task of attention layer that captures this relation between the words. So how the attention layer captures this relation, it's beyond this talk, but I really suggest, I will show you a source and suggest you to go and read the paper and you can see that how it can capture the relation between those. And here is the more detailed architecture of, full architecture of the transformer. Encoder gets some inputs. It has input layer, input embeddings. It also has a positional encoding that encode the position or relation of things, different words together. And then we have in a stack of these components. Each component has a mounted attention, as an attention part, and then comes a feed forward network. And then the outputs of the encoder part go to decoder. The decoder parts get the inputs, some outputs from shifted right from previous words, plus positional encoding, and then you have a stack of these attention, these decoder components. An attention layer, an attention, multi-attention from the previous that gets input from previous words. Again, an attention component that gets, we call it encoder, decoder, self-attention that gets inputs from the encoder part. And then we have the neural network, feed forward neural network. And after those stack of components, we have only just the linear combination. You can get the linear combination of them in the softmax, turning those linear combination embeddings to some probabilities that comes from 0 to 1 and then output it. So there are different types of transformer models. They're not all of them are not the same. All of them are not exactly consist of these two parts. Some of them may have only encoder parts. Some of them may only have decoder parts. So we have encoder-only models. These encoder models are good for tasks that require understanding of the text, because we want to encode the input text, and we can then use those embeddings if we just want to understand the structure of the input, the semantics of the input, and make some embeddings. And then we can use those embeddings for sentence classification and, for example, name entity classification or other tasks that only needs the input embeddings. Decoder-only models, they are good for generative tasks. When you want to generate some text, right? For example, just again remember that is typewriter. In the decoder models, we want to generate some text, like any kind of text generation models that we have here, usually called GPT-like models. And we also have encoded decoded models, or sequence-to-sequence models. They get some sequence of words in the inputs and generate some sequence of the words in the outputs. For example, translation or summarization are some of these examples of these sequence-to-sequence models. So, talking about a little more details with each of these models. Encoder models use encoder part of, only use encoder part of transformer. In that model, the attention layers can access all the words in the initial sentence. They are also called auto-encoding models because get the words, make an encoding, make an embedding of the words. For pre-training those models, we usually corrupt the given sentence and ask the model to somehow find the missing words or reconstruct the initial sentence. This is somehow like that a CBAW of architecture of virtual that we already done. And these encoder models are best suited for tasks that require understanding of full sentence, like sentence classifiers, name entity recognition, or extractive question answering. The question answering task that only answer your question through the given document and not generate an answer from itself. And some famous models representing these models are called BERT, Albert, BERT, Electro, and Roberta. And because of that, these encoder models are somehow called BERT-like models. The other way, we have decoder models that use only the decoder part of transformer model. And the attention layers can only access the word positions before it's in the sentence. They are also called autoregressive models. I will talk about this a little more about these autoregressive models later on. And for pre-training the decoder models, the task is that given a sentence, the task of the decoder needs to predict the next word in the sentence. So, as we already mentioned, that's suited for tasks like text generation, and because of that, they are also called GPT-like models. Famous models like GPT, GPT-2, Transformer X, GPT-3, and so on. And finally, sequence-to-sequence models that use both parts of transformer models. They are, in that case, attention layer of encoder, access to words in the initial sentence, and attention layer of decoder, access the words positions before a given word in the. So the encoder layer, attention layer of encoder part access to whole words of a given sentence, the attention layer of decoder access to only words that positions before a given. And there are best suited for tasks involving generating new sentences depending on the given input, like summarization, translation, or generative question answering. That you read a text, get some understanding, and then finish generate an answer based on that given text. Some famous models that are sequence-to-sequence models are BART, MBART, multilingual BART, Marian T5, and MT5. So here is a transformer history of transformer models. They started in 2018 with GPT, and then 2018 comes BERT, and in 2019 we have GPT-2, Robert, T5, Albert, and till 2020 that we have GPT-3, Berta, Electra, and nowadays that we have Llama, Palm, GPT-4, and so on. And here is the scale of those large language models based on the number of parameters that they have. And as the parameters, you can see that the number of those models at the typewriter, and each arm shows a single parameter of this typewriter. Here you can model it as a parameter of the model, and based on the data script that we have. And instead of long, sprite llama that has less number of parameters, we can see that in the span of our last 4 years, this size of large language models reportedly doubled every 3 months on average. So here is the mid or late 2023 this year, and you can see that each year the number of tokens, the number of sentences, and the corpus size that each of these models are getting almost getting doubled. And in the same vein, the number of parameters or the size of each of these. So as the last 2 parts of my talk, I just want to go very fast about 2 other concepts that you should know. One is transfer learning. The ideal motivation of transfer learning is that we have shortcoming of training data. Most task-specific data sets only contain a few thousand or few hundred training labeled claiming exam, right? But our modern deep learning based language models need millions or billions of annotated data, as we see in the previous diagram. So to close this gap in data, the idea is that we can train a general purpose language model that represents the relation of between words in that language. We call it pre-training, and then we can use a pre-trained model to fine-tune for a very specific small data NLP task. It's like that. For example, you know how to ride a motorbike, then you can learn how to ride a car. You know how to play classic piano, then you can learn to play jazz piano very easily. The idea is like that you don't need to learn everything from scratch. Transfer some knowledge, learn some knowledge of the basic knowledge of the field, and then transfer those knowledge to very specialized tasks. For example, you know math and statistics. Then, based on that, you can easily learn machine learning. So in traditional machine learning tasks, we have some single isolated task, but in transfer learning, you can learn a basic model and then use that basic model uh, for any downstream task. For example, in traditional NLP or traditional machine learning that we learn a separate model, for example, for text classification, separate model for text summarization, a separate model for main entity recognition. But here you can learn a general model that captures the relations inside the language and then fine tune that model for each of your tasks. For pre-training, you can use your data to learn the features and then use the features to do the prediction task, or can fine tune the raw model and then use that model and fine tune that model or another task. So here you can transfer the features that you learn from the model, so-called feature-based training, or you can use fine tune another model on the previous model that you learned. For the pre-training, you can have two different representations. What is called, one of them is called context. It's like that word-to-vec or graph models. In that case, for each single word of your language, so generate a single embed. For example, bank can have a single embed, can in the context-free training. In that case, bank would have the same embedding regard unless of its context. But it, as we know, bank can have two different meanings: bank account or bank of derivative. But for both of them, you use a singular. The contextual representation generates a representation, single separate representation for each meaning of those words. So here you would have two embeddings, two vectors, or two representations for the word bank. The contextual representation could be either unidirectional or bidirectional. In unidirectional, you represent a word based on the previous words. For example, I access the bank account. Here, representation of bank is based on its previous words. But in bidirectional representation, it can use the words before and after the word itself. I access the bank account. Here, being that the next word is account helps us to generate a better embedding for the word bank. So, what is fine tuning? Fine tuning is upskill a pre-trained model for a very specific task. So, based on generic data, for example, based on the data that we found on Wikipedia of the whole web, we first pre-trained a model that somehow captured the language, the relation in the language, or we call it language model. Then, for example, if we wanted to use that model for a very specific task, for a very specific domain, we can fine-tune it with that specific domain. For example, we want to use our model in the medical data, in the medical domain, we get a pre-trained model, then add some data from, for example, medical data, we fine-tune with our medical data for a very specific task. This is called fine-tuning. This is like that we have these screws. In traditional language models, for each single task, you have different screws, right? Screwdrivers. But for one the large language models, it's like that you have general pre-trained models that somehow capture the main functionality of the screwdriver. It somehow turned on, we should turn it on. And then for each specific task, you can fine tune your model with the task that you decide. And the last and not least part of the thing, the one is that I call self-supervision learning. Most of these large language models are learned in a self-supervised manner. In the self-supervision learning, there is no new need for human-curated data because we have a lot of billions of corpus of billion words of annotated data. Annotating or curating those data, labeling those data will take a lot of time and cost very high for us. But in some manners, we can use them as without any annotations. Two main tasks that can use as a self-supervision manner called masked language modeling and next sentence prediction. The masked language modeling, we mask out some of the words in input and then condition each word bi-directionally to predict the masked words. So we get this sentence: a quick brown fox jumps over the lazy dog. Mask lazy and fox and given the rest of the words to our network and ask it to generate or guess the missing words. Here we don't need any annotation, right? Because we already know the annotation from the word, from the sentence itself. Because of that, it's called masked language models. And just for your information, if you don't know before, this is a famous sentence that contains every single letter of English inside it, right? For every single letter of English alphabet, if you wanted to make a sentence, this sentence has one, every single letter appears once in this sentence. For example, you have one A, one Q, one B, F, O, X, Z, Y, B, O, H, E, and P, L, and you can find every other single letter in that sentence. The other task is called, so based on that masked language modeling, we have generative models like GPT models, right? These are called one special type of masked language models that we mask the last word or last token of the sentence and ask the model to guess it. And because of that, it's called autoregressive models because it's used its own prediction to predict next. Here, by regression, we mean that prediction. And by autoregressive means that it uses its own prediction to use the next prediction. For example, if you give the to the model, it generates the queen. Then it uses the queen to generate or predict sat. Then it uses its own generating sentence to predict the next one, and so on, and so on, and so on. And because of that, these models, which are specific kinds of masked language models, are called autoregressive models. And the final task is next sentence prediction. In that task, we give two sentences, A and B, to the model and ask the model to predict or guess that if, or decide that if sentence B should be the next sentence of A that comes after A or not. For example, Here I have, I'm going outside as first sentence. Then we give the model the inputs that the next sentence should be is I will be back after 6. And I said, is it the next sentence? Yes, it is. So the model used its own corpus without any annotation and outputs yes after that. So this task is using for this curated self-curated data is using for training the neural network online. Another way, I'm going outside. The next sentence is nothing. John Snow. It's no. It's not the next sentence in the sequence of this sentence. And here is the evolutionary tree of modern large language models. Started from 2017 and early 2018. Now still now that we are almost in the 2023. Thank you everyone. It was all that I would talk about today. Any questions? I'm here to answer your question. And again, thank you for listening to my talk.
Thank you, Said. Thank you very much. Very insightful. Even I learned a lot here. I was kind of like 0 to 1, starting from the very basics all the way to large language models. So that I do understand that the very last, like I would say 30 minutes is pretty evolved. So I would encourage you to go back. Hopefully we have this recording available and put it on YouTube and take another listen and look. But nevertheless, I'm glad I discovered here.
Yeah, just let me add one note that I just encourage everyone that so just go and read these two references. One is the first one is from Medium Blog, a very gentle introduction to large language models. And then read this one. After that, the Illustrated Transformer by J.M. Moore. This guy is very famous guy in this field that tries to make every concept very simple with a lot of illustration. And also after that, if you want to go do your own codings, just go to this Hugging Face library. The Hugging Face library of companies like trying to put every model in a very simple format that you can use only 5 to 10 lines of code and use to training and using those large language models. So I encourage everyone to, after watching the talk, just go and read this blog and then check JLM illustration in the its own website.
Yep, definitely. Any questions? I can like stop the recording, or any questions from Said?
I have one question.
Sure.
So does NLP has much potential for development in the future, or it is almost completely technology? I just wonder.
Definitely. I mean, you can see that, for example, all of these today's large language models, like GPT-4, something like that, these are going to be multimodal, right? These are not. These are trained or using a pre-trained models based on language, but nowadays they are as their inputs accept images, videos, voice, something like that, right? And so definitely there will the lot of other applications, not only language-based applications, but in any other fields for the future of AI. But most of them can somehow rely based on NLP tasks. Because, for example, most of the tasks are based on transferring some concepts, right? And for transferring the concept, you use language. You need to communicate, and for communication, you need to somehow understand the language of the spoken task, right? In any specific task. So all of the text somehow depends on your understanding from the language, and for that you need to know and use the NLP-based models.
Thank you.
Any other questions?
Yeah, I actually have one question, Dr.
Sure.
Majidi. Yeah, so I'm just wondering, I know you kind of mentioned it, but like for models like ChatGPT, how do they do data cleaning? Like what they know not to learn and what to learn?
That's a good question, actually. First of all, you can somehow go to this, after reading this blog, you can see that how it works actually more specifically, ChatGPT. And I was going to actually bring a slide about it, but I somehow forget about it. But I can talk about a little about it to this. One thing that makes a ChatGPT more specific from other models, and as you let me go back these slides. I just want to show you. Anyway, I just want to show you that slides regarding the this one. The history of these large language models, right? The history of the history of these language models. And we talked about it. The start was in 2017, right? From 2017 till 2022, the end of 2020, that ChatGPT was released. There were a lot of other language models, right? But what was specific with ChatGPT that makes it very famous? This is the one that it somehow tried to train its model based on. First of all, does it do some kind of text cleaning or pre-processing? In some sort, no. Most of these language models doesn't do any sort of cleaning by cleaning and pre-processing. I mean that's removing extra unwanted characters like punctuations. You somehow use actually those punctuations because even an exclamation or a question mark has its own meaning. All of these language models have a specific part inside them. They call it tokenization. So they get the sentence tokenized, and each one has its own way of tokenization, converting each word of a sentence into a separate token, right? For example, if I have a sentence that I've been there, the tokenizer can tokenize it into 3 tokens, I've been and there, but another tokenizer can tokenize that I've being there. So the first word I've can be tokenized into different manners. And each of these language models has its own tokenizer. So they do some cleaning in sort of removing unwanted words like stop words or punctuations. No, they use them, but they somehow do some tokenization. The second question is that, okay, how ChatGPT use the text to, what are the other processing? We don't, ChatGPT for training doesn't do any pre-processing, but it does do some post-processing, right? For the post-processing, it takes two different approaches. One approach is called reinforcement learning human feedback. By reinforcement learning human feedback, I mean that when you give it a prompt to the ChatGPT, it can generate different answers for it, right? So the guys in OpenAI, the company that ChatGPT was developed, they hire some other people, some humans, about 40 humans, and their task was that, okay, give a prompt to ChatGPT, get the answers, and then rank those answers as most related to the prompt to the least related to the prompt. So in that case, they give us some sort of feedback to the model that, okay, your first question, second question, third question, your third question is most related to my prompt. So put it first, your next time, then, and after that. Another task is like that instruction learning. For instruction learning, for example, if you give a prompt to the ChatGPT and I said, please write me 2 pages documents about language models. Most probably at the first place, it will generate the generated text as your generated documents should be 200 words, 1.5 line of space. It's not related to large language. But why it happened? Because it learned from the previous text inside its training data. And in most of the previous text in your training data, when somebody asked to write a paragraph, a document about any subject, it also adds your writing should be 200 words and 1.5 line of space, something like that. So to somehow correct that answer, again, it's hired some group of human people to give it, to somehow guide the output of its prompt to some proper formats, right? And based on that, ChatGPT doing some post-learning, some post-processing of its output, it could now get better results. The main one is, as I told you, reinforcement learning human feedback. Some people sitting there for each prompt, not now, but in the learning phase, and it was developing phase, where they are developing or training their model, and generate a separate model based on the feedbacks of the human and the players. Okay.
Yeah, thank you so much.
I think we should invite you over again. So at some point to have another talk here. Okay, let me stop there. Thanks again, Dr. Majidi, for the great discussion and talk here.
I'm happy that see you some of you guys again, and thanks again